Okay, now it's recording. We can say that the specific volume is the inverse of density. Density, we usually write density as like that. And specific volume is like that. Okay, for example, if you have the tetrachloride, carbon tetrachloride, this is having the density. Density is gram over centimeter cubes. And if it has the volume 20 centimeter cube, what is the mass? So it's simple. You already know how to calculate, but my suggestion, when you try to calculate this, write completely with the units. Sorry, this should be okay. So mass, and then multiply with the density, and write completely with the unit. Okay, I think it's simple enough to see that this will be 31.9 gram. But what I want to emphasize is writing these units. Okay. Later on, more and more formula and more method, it will require you to focus on the some objective in some case or some study case, and this will probably become more longer and longer. And the idea is still the same. Keep on your units to keep in check, okay? To keep in balance on all the calculations. Okay. Another terms that is important on this subject is the specific gravity. Okay. Specific gravity is the ratio of density of the substance to density of reference substance, or just reference, okay, just reference. So we'll usually write as G is rho divided by rho reference. So basically, because this is just a ratio, it doesn't have specific units. It's not having any dimension. But it's stated some ratio, some numbers. Sometimes it's written like this. Maybe 1.595. This is 20 degrees Celsius. This is 4 degrees Celsius. This means that the reference is at 4 degrees. Okay. Our density or our specific gravity is on 20 degrees. Sometimes we write like this, but this is, I think it's more traditional, conventional. Usually in our textbook, we just directly write without any dimension or specific gravity. Or, oh, I think your textbook also mentioned that. We can write this in terms probably like this, and then 20 degree, 4 degree. Okay. This is just a notation, to know that which one is the reference. Okay. And usually the reference is water 4 degree, because that's easy to be measured. And usually for some specific gravity, we will use some table to help. Like in your appendix in the textbook, there will be a table B1, B2, and etc. The specific gravity can be observed on table B1, which has listing some chemical compounds. And usually in exam, you need to prepare like a bundle appendix from B1 to some, I think B11, until B11. Yeah, and you are going to use that in some calculations. Like for example, some calculation required some constant from those tables, and sometimes the question didn't really mention those numbers, so you need to find the numbers first. Okay, that is the mass and volume. Okay. Really the basic one. Another way that I want to show you is the flow rate. Which includes mass and volumetric. Usually it's drawn like this to denote that there are some flow. We can have a mass, which is like this, the symbols. We call this kilogram fluid. Fluid per second, or just kilogram per second. Okay. Because the picture already denotes that this is fluid. And we have the volumetric. Okay. This means that this is actually mass over time, and this is volume over time. And usually it's drawn like this, and this is to like if you want to imagine this is like a pipe, and you have like a gas or a fluids or any viscous fluids or gas also, you can imagine like that. And this is the cross section of the pipe. And the key in the flow rate is the density. Okay, the key is the density. Okay, which means that because density is in every substance will be the same, right? Whenever whatever the amount of substance, so we can convert the volumetric or the mass flow rate with the density. Okay. So we can write this as mass over volume, still equal with the flow rate. Okay, there's some description on the textbook, but I think the description can be observed through these equations. Yeah. So the density can be used as a conversion. Okay, now to measure, we can use it's called the flow meter. The first one is called the rotameter. The right one is called the orifice meter. So the first one, I think is intuitively can be understandable. You can see the point, it can be changed, but it depends on the flow rate. And for the second one, you see the difference in the pressure or difference in the height. It's similar to what we call manometer. Later we will learn about the pressure, but it's similar. Okay, similar. Okay, I don't think this is important. I think I can just show you the essential variables that are in our subject. Okay. The third one is actually it's chemical composition. So the first one is actually about mass and volume, and also the flow rate of mass and volume. Right? The second part will be the chemical composition. We will learn about moles, molarity, and so on. Okay? So moles, I think everyone familiar with that, and molecular weight. The first definition is the atomic weight. Okay, so atomic weight of an element. Okay, let me write this. Mass of an atom on a scale that assigns the isotope of carbon. A mass exactly 12. This is practically the exact definition of the atomic weight, that you need to have some to scale the isotope of carbon, which have the 6 protons and neutrons, and it should have exact number 12. And the molecular weight is the sum of the atomic weight that atomic weight of the atoms that constitute a molecule of compound. Okay. I think you already, without the exact definition, you already know that if you have oxygens, which means that this has 2 oxygen, and that's why it's 2, 16, it's 32, right? Okay. So I think doesn't really need to have some subject. And of course, this is we can apply or we can find in table B1. Yeah. Some of the chemical that is frequently appear in the textbook. And of course, the units on molecular weight is the gram over mole. Okay. Oh, gram mole, sorry. And gram mole, if you convert to using Avogadro numbers, so 1 gram mole will be 6 molecules. This is the Avogadro numbers. And also the molecular weight can be has some relations to the flow rate.
can be used to relate the mass flow rate of a continuous stream to the corresponding molar flow rate. Okay, if let's say example, if molecular weight of the CO2 is 44, let's say it flows through pipeline at 100 kilogram per hour. So the molar flow rate, or let me write in terms, let's just write molar flow rate. This will be 100 kilogram of carbon dioxide, say per hour, then multiply with 1 kilomole of carbon dioxide divided by the molecular weight, and you see that we have units cancel, so we will have 100 divided by 44, that is around 2.27 kilomole per hour of the unit of carbon dioxide. Okay, so again, the conversions or the units is pretty important here, especially if the units are not in the same, or you need to convert to another unit, then you need to also apply this calculation so that your calculation will be having, or your calculation will be more meaningful, and you get the final objective of your goals. Okay. Okay, so aside from the molecular weight, the moles, another important terms is the average molecular weight and the fractions. They are also important. We can have mass fraction or mole fractions, because sometimes we are going to observe, like maybe it is like a really long compound and we are only consider one element that we are going to measure, right? So mass and mole fractions. It's, I think you already know this one, but let me just review for you. This means that mass fractions. Let me write, this is mass. Okay. Mass of A divide the total mass. We can say that this will have kilogram of A over kilogram total. And we can also write in terms of mole. Usually it writes as Y like that and having A. So this will be moles of A divided by total moles. Let's say we have a kilomole A over kilomole total. And of course, if you are writing in terms of percentage, then if it is percentage, then this will be 100 XA, this will be 100 YA, right? Okay, and I think I can give you this example, and I hope we can finish until the molecular average molecular weight, but I don't think we can have. But let me just give you this example. Mixture of gases has composition. Said oxygen 16%, carbon monoxide is 4%, carbon dioxide is 17%, and nitrogen is 63%. And the we can write this mass fraction is 0.16. I think easy to calculate this. Oh, sorry. 0 oxygen over total. Okay, the question is molar composition. We can write in a table. I think it's quite convenient to divide some into some column, row and column. So this will be a component. Let's say this is a mass fraction. Start with 0.16, 0.04, 0.17, 0.63, right? And the mass itself, we can calculate by 100%, right? So we are having 16, 4, 17, 63. So the total will be 100. And molecular weight, let me just write molecular weight like that. This is 32, 28, 44, 28. And then moles, this is 0.5. Okay. This is 0.143. Or I can write the formula here. This is and then lastly we can write the mole fraction. This will be n divided by n total. The total, we can plus this first, so we can adding all the moles. Oh, I forgot to add. This should be 1. This should be 100. And then we can calculate the fraction for the mole. So each one will be divided by the total moles. So it will be 0.150, 0.044. In which we need to make sure that this is also 1 in addition. Okay, I think I will stop after here. So in terms of some mixture of a component, sometimes you need to write in a table so that you can make sure that, for example, the mass fraction should be 1, the mass is 100 because we are using percentage. This is the molecular weight. The moles, this is the total moles, and we are going to use this to take into our mole fraction to have our composition in mole. Okay, I hope this still have familiarity with you. it's more about chemistry. Okay, so let's meet up again next Thursday. And we are going to finish off the chapters. We are just a few sections, okay, up until the last one. Okay, but be prepared for if there is a quiz. Okay, be prepared.
Thursday still maybe there's
Maybe.
Sorry. How about like chapter 1? Is it still included in the quiz? Chapter 1? What's it about?
I think chapter 1 is just introduction. So I think more about chapter 2.
More chapter 2.
Chapter 2 and a little bit chapter 3.
I mean, it's about like in chapter 2, like we learn about significant figure or something.
Yes.
Like chapter 1 is like, I mean, like.
It's just definition.
Should we get memorize that one or?
I think more about chapter 2.
This calculation.
Yes, the units, like how you write the decimals,